This video is going to illustrate the use of evaluation models during the component selection stage based on a case study. We are going to focus our study on an example of elevator modularization. There are currently two types of elevators on the market, the hydraulic ones and those who work thanks to a cable. Those technologies both have pros and cons. Among most obvious one, for hydraulic elevators they are easier to build but require more energy to work. For traction cables ones, they don't require that much energy, about a third of the hydraulic ones, thanks to counterweight, and maintenance operations are less constraining because there are no oil leaks. These days, we generally choose traction elevators to optimize energy consumption of machines. The objective here is to set up evaluation models for the brushless motor and the reducers. This example will allow us to illustrate how power plants can evaluate the working condition of components. It's necessary to verify that the components we elected can work in a durable way under our mission profiles. Two types of degradations are generally encountered. Sudden degradations, corresponding to efforts and speeds exceeding the admissible limits by the components. It's therefore necessary to check that the mission profile remains in a valid domain of use for the component. And slower degradations, like mechanical fatigue, characterized by an accumulation of damage, progressively leading to the component's destruction. It's necessary to calculate equivalent quantities that could represent these deteriorations. The specifications for carrying the load include dynamic requirements. Acceleration and jerk specifications are given by the comfort and physiological limits of the users. Liability and lifetime requirements. Dynamical specifications can be represented in a typical mission profile for the use of the elevator, composed here by a chain of ascents and descents. This 65-second cycle will be repeated in a continuous way 8 hours a day during 10 years or 30,000 hours. This is the required lifetime of the reducer we use here. The mission profile generator, completed by a second-order filter, can allow us to impose a certain movement to the mass which represents the elevator shaft. The carrying mechanism is realized thanks to a pulley in a counterweight. We neglect here the effect of the mass variation due to the cables. The counterweight compensates the weight of the shaft when it's half-loaded. The computation of torque and speed of the pulley can be done by using inverse simulation or by implementing calculus in MATLAB or Excel. These graphs give power and torque quantities for three load configurations: empty elevator, the shaft weighing 400 kilograms, half-loaded 700 kilograms, or fully loaded 1000 kilograms. After obtaining these results, we can already infer that our system requires efforts and speed both positives and negatives, which implies that the motorization will have 4 quadrants. The power can be positive or negative as well. Power electronics will have to deal with this reverse power, either by making the system fully reversible or by dissipating power in a resistor. The most constraining case for power remains the one where the elevator is fully loaded. We will use this case in order to size the actuating chain. Maximal speeds and torques are about 55 rotations per minute for this cycle. The motor will have to be associated to a reducer in order to have such high torque, low speed characteristics. Operational limits of a synchronous motor with permanent magnets are divided into two types. Transient. There is a maximal torque because of magnetic saturation and a maximal speed given by the alimentation voltage. We must make sure that the emission profiles for torque and speed remain in the admissible domain. And continuous. The torque is limited by the copper losses and the winding temperature. This mean temperature depends on the average of losses depending on the effective current itself depending on the effective torque. In conclusion, we have to be sure that the effective torque, or root mean square of the torque, RMS torque, is below this continuous limit. Operational limits of a reducer are also divided into the same two types. Transient, the torque is limited by elasticity limits of the materials and the maximal speed by centrifugal force. And continuous, the torque is limited by the bearing's fatigue, which besides increase with rotation speed, if we consider that the degradations accumulate in a linear way. Proportionally to the number of spins, we are able to calculate an equivalent torque for a complex mission profile. We call it the root mean cube torque. To calculate mechanical fatigue in a general way, we have to proceed in the following steps. Based on the mission profile's torque and speed, we compute equivalent mean fatigue speed and torque, which are RMC torque, and the average absolute value of speeds. If this average speed doesn't match the average speed specified in the catalogs, we determine, thanks to the minor Palmgren law, an equivalent rated torque that will associate to the rated speed of the catalog. Based on the mission profile of the reducer's slow axis, we're able to determine maximum speeds, maximum torque, mean torque RMC in fatigue, and the corresponding speed. For a reduction ratio equal to 61, the average speed is about 1106 revolutions per minute on the low axis. However, it doesn't meet the 3000 RPM average speed declared in the catalog, which is why we recalculate a rated torque equal to 833 Nm, lower than the RMC torque, by taking into account the lower number of revolutions to execute over its lifetime. We are now able to choose a reducer slowly superior regarding the average torque. We'll verify that it's also able to ensure the maximum torque required in the specifications. The reduction ratio has been determined so that we use the motor on a pretty high speed, but still acceptable, allowing us to diminish the motor torque, thereby reducing its cost and mass. To ensure a 61 reduction ratio for the reducer, we calculate an RMS torque of 13.2 Nm, which can be supplied by the chosen motor itself with a 60 Nm continuous torque. The same motor can deliver a maximum speed and a maximum torque compatible with our application. So finally, we can confirm the component's choice.